And welcome to another video. Today we're going to be doing lowest common ancestor of a binary tree 3. So given two nodes of a binary tree, P and Q, you want to return the lowest common ancestor. And each node will have a reference to its parent node, where we have the left, the right, and the parents. Looks like here they gave us a definition of LCA on Wikipedia. Okay. And here they give us an example tree. The least common ancestor of the nodes 5 and 1 is 3 because it's the least common ancestor, it's the smallest one. Same thing with this one. Output is 5 because the least common ancestor of 5 and 4 is 5 because they don't really have a common ancestor, and the very top one is going to be 5 over here because, like, it can be a descendant of itself according to the definition on Wikipedia. Looks over here. Okay, this kind of makes sense. All node values are unique, and P cannot equal Q, and P and Q exist in the tree, so we don't have to check for any of those constraints. Any of those constraints. So I guess this kind of makes sense. This problem is a little bit easier, I think, because we have we're allowed to go move up to the parent. So I think we can utilize that to our advantage. An idea which I have right now is, let's say what we can do effectively is we start off at the P and the Q. So we start off at 5, and then we start off at 4, what is it? Oh, 5 and 1. Yeah, so we start off at 5 and 1. And then the easiest thing to do would be to traverse up its parents, so it keeps going to its parents up until you encounter until they're both equal to the same thing, whereupon you can just return either one because that's the final answer. So that'll work for this situation. So we have 5, 3, and 1. It'll work for that. So 3, 5, 1. We move up the parent, and this we have 2 pointers, right? So we have 2 pointers. 1 is going to be equal to 5. 1 is going to be equal to 1, and then we keep moving this forward up until we hit the parent. So I think that's relatively straightforward. The one where it gets a little bit more complicated is where we have the 5 and the 4. So for the 5 and the 4, what we can actually do is we can move the parents forward as well. But the unique thing that we're going to have to do in order to make sure that it hits the same place is if we have 5 over here, we have 4 over here, and as soon as you move the pointer for 5 up to 3, and you move the pointer for 4 up to 2, you'll notice that 5, the pointer where 5 was originally, the pointer currently at 3, it can't go anywhere because it doesn't have a parent, right? So what we can actually do is we can reset it to the origin of where Q where Q was, right? So we'll convert it and we'll make this 4 again. So the parent of 3 effectively, or where we want it to go for our next step, is going to be equal to 4. Now, I'll do a quick dry one of this just to verify that this works. So we have 3, 5, 1, and then we have I'll just 6, 2, 7, and then 4. So I'll put this here. 7 and then 4. So from here, we can actually take a look. We don't have to draw this part out because it's not super relevant. But what we can do is we'll start off with the pointer here. Let's denote the pointer with an underscore or whatever, and we'll start the pointer off at 5 here as well. So for here, our first iteration, we move the pointer from 5 to 3, right? And for this one, we move it from 2 to 4. Now, this would work normally for this case because then it would just be equal to each other and we could return the final result, but it's not equal right now. So what we need to do is we need to move this forward again, and then we can set this and have this reset back to where the other node was originally. So this becomes 4. And eventually what's going to happen is because it sets it back, it's going to set it back by the difference between the nodes originally, right? So it's going to happen again. You're going to move this again. You're going to move this again, and this is going to go here. This is going to go here, and it's going to keep moving forward. It's going to reset backward, and it's going to keep moving on eventually. With this here. Yeah, it's going to keep moving on eventually until eventually it'll converge and it'll hit the same value at the very end. I think I might have messed up the top the underscoring a little bit, so I'll just restart from scratch. But I really want to just like show this visually. Okay, iteration 0, we start off at 5 and we start off at 4. We move the pointer forward. So this is the end of the iteration. We move the pointer forward again. And then this becomes it. We move the pointer forward again. And then this becomes like this. We move the pointer forward again. Yeah, we move the pointer forward again. And this becomes this. And then we move the pointer forward again. And then it comes this. Wait a minute. Oh, shoot. Sorry. This needs to go to the... I was thinking really wrong. We actually need to make it go to like the other parent. So we have 5 and 4, and we know that after this gets to the top, we want this to go to the 4, and after this gets to the top, we want this to get to the 5. So we move this, starting at iteration 0 again. We move this to 3, and then we move this to 2. And then the next thing we do is this one goes to 4, and then this one goes to 5. So I guess to kind of, yeah, and then we move this to 3, and then we move this to 2, and then where this one ends up going is back to like its original. So it ends up moving to 3 over here, right? Because it goes to the other node's original one, and this one ends up going to 5, and they both converge after at maximum 2 iterations of this. So this is going to be the lowest common ancestor, and this is what we're gonna have as our final result over here. And like the way this works is it kind of closes the gap in terms of the distance between the two ones every single time you reset it back to its parent node, so that it'll eventually converge and reach the same point in which that will be the common ancestor. So maybe this will be like a little bit more explained thoroughly through code, so I can go ahead and begin implementing it. While p not equal to q, we want to set the p1 p equals p dot parents, or well actually we'll set like the 2 pointers p1 and p2 equal to p and is equal to p and q, because we want to still have references to the original pointers. So while the pointer 1 isn't equal to the pointer 2, p1 is equal to p1 dot parents if p1 dot parents, else p2 is equal to p2 dot parents if p2 dot parents, else p. And then after this one we can return our final result, which is going to be just either p1 or p2, doesn't matter. We'll go ahead and run this. Okay. Let me think. Oh shoot, I forgot this typo. Okay, there we go. So this is kind of the algorithm and how it works. In terms of the time and space complexity of this one, it's going to be O of n. O of n time. Actually, yeah, it should be O of n time the worst case, because it could be a scenario where it's going to iterate through every single element in the tree before it's able to find the lowest common ancestor. And the space complexity is going to be O of 1, because you're not actually storing anything except those 2 pointers. You're just going to keep moving up in back and forth through our algorithm. So yeah, final time complexity O of n, and space complexity is going to be O of 1. Let me just quickly submit to verify this works. And yes, it is. Thank you guys for watching.